Hi, I'm Nazmul. In this tutorial, I'm going to show you how to design a cylindrical dielectric resonator antenna in HFSS. For the CST users, you can also find another CDRA tutorial in my YouTube channel where I showed how to design it in CST. Before starting the design process, let's have a quick introduction to dielectric resonators. So these are very weird shaped materials that can be resonated if excited electromagnetically, and the resonance frequency would be dependent on the shape of this material, and also it depends on the type of excitation that you're giving. For example, you can excite these materials by using microstrip, aperture, or even probe. So different excitation types would generate different modes inside these resonators, and then you will have different resonance frequency. All right. And most of these materials, most of these resonators do not have closed form equation of resonance frequency. So it's basically determined by using numerical analysis and some kind of curve fitting method. Anyway, so let's proceed to the cylindrical dielectric resonator antenna, which is the main focus of this tutorial. So when you construct a cylindrical dielectric resonator antenna, we place it on top of a substrate, and then we can excite this CDRA, which is the short form of the cylindrical dielectric resonator antenna. So we can excite this CDRA by using a microstrip line. This CDRA is coupled electromagnetically with this microstrip line. All right. And below this substrate, we have a full ground plane. So no radiation happens below this substrate. All the radiation is right on top of the cylinder. So if we assume that the cylinder has a radius of r and a height of h, then the resonance frequency can be roughly calculated by using this expression. But again, this expression is only valid for this hybrid mode, which is denoted by HEM11 delta mode. Now, you should also be aware of that this same cylindrical dielectric resonator antenna can be excited by using different modes, for example, transverse electric or transverse magnetic modes, and then you have to calculate the frequency of those modes with different expressions. So what determines that which mode is generated? The answer is the excitation type determines that what type of modes are you generating in the dielectric resonator. All right. So you can excite this same cylindrical dielectric resonator by using a probe or by using an aperture. Then you would be able to generate those transverse electric and transverse magnetic modes. All right. Anyway, if you want to know more about the dielectric resonator antenna, you should be able to find the material online, or even you can just look it up in any textbook. So if we see the formula, we have an epsilon DRA, which is the permittivity of the dielectric material, which is usually very high, and c is the speed of light. Now, if you assume that the radius and the height of the cylinder is 10 millimeter, and if we use an aluminum ceramic, which has a dielectric constant of 9.9, then the calculated resonance frequency is 4 gigahertz. All right. In our HFSS design, we're going to use these parameter values, as you can see, which are written in the table. And The substrate that we're going to use is Rogers RT5880, and the cylindrical dielectric resonator material is alumina ceramic, which has a permittivity of 9.9. So let's begin our design process in HFSS. Open a new HFSS project file and then create a new substrate. Let's name it substrate. We're going to use Rogers 5880 substrate. Rogers, yeah, this one. Okay. I don't like green color at all. Okay, fine. Now let's define the dimensions. So the length is 60 millimeter and width is also 60 millimeter. SL. And along the z-axis we're going to define the thickness SH, which is 1.52 millimeter. Fine. Looks great. Now let's define the ground plane. Let's name it ground. Let's change the color as well. And let's make sure the dimensions are perfectly equal to what we defined for the substrate. SL by 2. This is stable negative. Stable by 2. Stable, sorry, this is SL. And this is SW. Okay. We also need to define this ground as the perfect electrical conductor. So simply define the boundary as perfect E. Great. Now we are going to shift this coordinate system along this H. In order to do that, go to modular and then coordinate system, create relative CS and an offset. Select this point. So this is the newly created coordinate system relative CS1, and we're going to make sure that this is perfectly aligned. No room for confusion. You should always make your design parameterized. Alright? Fine. Let's also move this coordinate system upward by the thickness of the substrate. So in order to do that, just add this SH value in the Z component. SH. This is the thickness. Yeah. Now it's moved. Now let's create the microstrip. There you go. Let's name it microstrip and then change the color. Let's also change the dimensions. Along the x-axis we're going to define the width, so it's negative MW by 2, and along the y-axis we're going to define the length, and the width is 4.65 millimeter. Sorry, this should be MW. This is the length of the microstrip, which is 40 millimeter. Okay, fine. Now let's again translate this coordinate system right into the middle of this surface. So go to modular, coordinate system, create, and then offset, and click anywhere in this surface because we're going to eventually realign it. So the X component should be 0 and the Y component should be half of the width. Okay, great. Now let's create a cylinder. Let's name it CDRA, and the material for this cylinder is alumina, and HFSS basically treats this alumina ceramic without any loss tangent. You can see the dielectric loss tangent value is 0, right? So what we're going to do, we're going to modify the property of this material. In order to do that, just first clone this material first and then rename it alumina ceramic. And also we need to change this relative permittivity to 9.9 and the dielectric loss tangent 0.0001. Okay, I don't like green color at all. And now let's define the dimensions. Radius rad, which is 10 millimeter, and height h, which is 10 millimeter. Okay, fine. Looks great. Now I can see the microstrip is not assigned the perfect E boundary, so just do that. Perfect E. Okay, fine. Now we have everything, substrate, ground plane, microstrip, and the cylinder. Now two more things are remaining: radiation box and the port. Let's name it radiation box. Let's change the transparency so that we can see the antenna inside. Okay, and now let's define the dimensions of the radiation box. Now one particular note I'd like to share with you is that HFSS by default uses absorbing radiation boundary, not PML. So what's the difference between PML and absorbing radiation boundary? The difference is that PML can, let's talk about the absorbing radiation boundary first. You need to define the size of the absorbing radiation boundary in such a way so that your antenna is located at least quarter wavelength at your operating frequency from any surface of the radiation boundary. So the distance between the radiating structure to any surface of the radiation box should be at least quarter wavelength. Okay, and as for PML is very intelligent and it doesn't need this condition. So even a smaller size radiation box, PML can work without satisfying this criterion. Okay, so but using PML is a resource consuming. For example, it would take a lot of space of your RAM and CPU resource. So for quick simulation, you should it's better to stick with radiation, default radiation setting of the HFSS, which is absorbing radiation boundary. So the conclusion is that you should define your radiation box in such a way so that your antenna is located at least quarter wavelength from any surface of your radiation box. Okay, so I'm going to define minus 60 millimeter, and here is 60, So it should be 120 millimeter, 120. And below the radiation box, because below the surface of this substrate we have a ground plane, so no significant radiation happens below the substrate at all. So we can define less area below the substrate for the radiation box. You can define, like, let's say 10, but in the top direction the maximum amount of radiation is going to happen, so you're going to make sure that you have enough room in the top. So let's take it 50. Okay, so sorry, I incorrectly defined the negative of the z-axis. It should be negative, but I gave positive. Do you see that? It should be negative. Okay, now it's fine. Now we're going to define the radiation boundary of this vacuum box. So right click on it and then go to assign boundary and then radiation. Okay, so the last thing is to define the port. In order to do that, you have to select the coordinate system, which we define along this edge, which is relative CS1, and then let's define a port. Okay, so the working plane, the grid is along is on the XY surface here, but we have to define the port on XZ plane. So just change the grid to XZ plane. Alright, now it's fine. Now we can define the port. Just define any square, because we're going to enter the dimensions manually. Here it is. Can rename it port, and let's change the color. Now let's define the dimension. We're going to make the width of the port at least 10 times the microstrip width. So it should be -5 times MW, and along X size it should be 10 times MW. Okay, and we're going to make the height of the port at least 8 to 10 times of the height of the substrate, the thickness of the substrate. So let's define first negative SH, and then the Z size should be 8 times SH. Okay. Another important thing that I'd like to tell right now is that if you notice, the port is located inside the radiation boundary. Okay, but HFSS doesn't allow you to put your waveguide port inside the radiation boundary. It allows you, but you have to define a PEC cap, which is essentially a metallic thin slab attached to the back side of the port. Okay, otherwise you are going to get error message when you're going to simulate this structure without defining a PEC cap. Okay, so first let's define the PEC cap, which is essentially a metallic slab, thin slab attached to the back side of the port. So just click on that and let's define this PEC cap. There. Let's name it PEC cap. Let's change the color to blue. and the material should be PEC, which is perfect electric conductor. Alright, let's change the size of this PEC cap, which should be equal to the port. So it should be -5 times in W, and it should be SH. It should be XI should be 10 times microstrip width, and Y is the thickness of this thin slab, which should be very small. So let's say it's 0.5 millimeter. And the Z should be 8 times the thickness of the substrate. Okay, fine. Now we have these structures and all the materials and elements that are necessary. Nothing to define now. Only one thing is remaining. We have to define the port. So let's define the port. Select this port and then go to assign excitation and waveguide port. Select the integration line from the ground plane, middle of the ground plane. It should be, yeah, this triangular symbol means you have selected right the middle point of this edge. So the integration line should be directed from the ground plane to microstrip line. And then press next. We have to renormalize all the modes to 50 ohm port impedance. Finish. Fine. Now you have everything. Okay. Let's double check. This is ground plane, this is microstrip, and this is radiation boundary. Okay, and this is our port. Now let's go to add solution setup and go to advanced. Our solution frequency is 4 GHz. Should make it at least 20. The lower this number is, the better, but it should also elongate your simulation time. 0.02 is fine. We're going to use discrete sweep type and make sure your frequency range is 3.5 to 5 GHz because this antenna resonates at 4 GHz. And I'm going to use linear steps with a step size of 0.2 GHz, 0.02 GHz. You should always enable this option, otherwise you cannot see the radiated far fields and other important things like electric fields, surface currents. Alright, although it consumes memory, but in order to check those parameters you should always enable this option. Okay, now let's go to radiation and define a far field. Make sure you just select from -180 to +180 for the theta, and for phi 0 to 60 degree. Step size is 2 degree is fine, and the curve will be smooth. If you use larger step size here, like 10 degree, the radiation plot and the polar radiation plot would be very coarse. I think 2 degree is fine. Okay, now we are ready to simulate our structure, and before starting the simulation you can validate your design. That means everything is fine. Now let's start the simulation. So the simulation is running. I will pause the video and come back again once it is done.